say something now.
You mean all my good stuff was... I can rewind, rewind it? Anyway, so it's been great fun. And one of the things that impressed me when Andrea was asking for sort of an abstract of the talk and so on is that she went online and found all of this stuff about me, anyway, and so I was incredible. You know, some of these interviews. I mean, I thought, man, I've just, and so it's gotten to the point where you really have to watch out what you say and when you say it. And a beautiful example of this was at the end of last semester. I had a final exam that started at 7:30 in the morning in December. Okay. And so just to sort of voice in a general sort of way of my feeling about the whole thing, as I came to the exam at 7:30 in the morning in pajamas and bunny slippers. And that was okay, except that somebody had a smartphone. Okay, and you can actually access this picture, and with comments too. I mean, one of the comments was that this is what tenure looks like. And so on it went. And so, in any event, it's just been great fun. And you know, people ask me when am I going to retire, and you know, it's probably in a couple or more years, or as long as my health, fortunately, has been very, very good, and I've been very blessed that way. And it's as long as it's fun. I mean, young students, I mean, they keep you on your toes, and you have these cheating conspiracies, you know, that you have to figure out. I just had one of those this last time, and so they keep you on. I mean, you're dealing with people that are on their way up, that they're very energetic. This contrasts with doing social work or police work, where you're dealing with, you know, by and large, the dregs of society, and it's a whole different. I mean, I applaud those people. I mean, they're doing God's work basically. So anyway, I've been very blessed. I've had a lot of. I mean, I could sit down over a pitcher of beer and tell you all of the lucky breaks that I've had throughout my years on the planet. So at any rate, what I'd like to do tonight is to talk about, as Andrea said, the Global Network of Astronomical Telescopes, or GNAT. And up until the early 90s, I used to get observing time fairly regularly at Kitt Peak, but was on the small telescopes, the number 2 36-inch, 16-inch. And so did a lot of my colleagues. And so in the early 90s, there really was a fundamental change in the attitude of astronomy. Okay, and let me put some quotes up here. The names have been deleted. Okay, Andrea might recognize some of them. But the first one is, it's not possible to do astronomical research with a telescope smaller than 3 meters in aperture. Okay? And my colleague Eric Crane says that that's been up to 8 meters now. You have people out there that are saying that. Second one, big telescopes are getting 99% of the astronomical funding, and we want all the rest. Okay? And then, in a more recent one, in the future, the default place to look for astronomical objects is our database and not the sky. Okay? And then my favorite of all is Roy Tucker, one of the GNAT members. Anyone can find something with a 10-meter telescope. And so, in essence, what happened, at least at the national observatories, the NOAO shut down all the small telescopes. And that basically put me out of business. It put a lot of my colleagues out of business, because we were doing projects where instead of competing for, let's say, 4-meter time, where let's say you get a week, and boy, that's a big chunk of time on a 4-meter, and you maybe out of that you get 2 or 3 nights of usable data. Okay, I could get on the number 236 or the 16-inch, and I could go for 2 or 3 weeks at a time. And boy, you can do some really nice stuff under those circumstances. So the question then is, well, what are we going to do? You know, how are we going to keep doing astronomy? I mean, you know, a lot of people just curled up and died, okay, in terms of their astronomical stuff. So like most organizations, these started out in a bar. Okay, this is down in San Diego. Okay, it was during a AAS meeting in 1992, and some of our, let's see, how does the
just right in front of the back and forth. There's a button
right here.
Right, just this one right here.
Oh, okay, good.
Right there.
Oh, there we go. Okay, so this is Eric Crane. You'll see him a little bit later on. Dave Crawford is a very famous photometric astronomer who was one of the people who invented or developed the H-beta index for photometry. Phil Ianna, who is very much in, works in parallax measurements. He's retired now. And then Mark Giampapa, who is a solar astronomer, but is interested in solar-type stars. So this is only a part of the cabal, okay, but this is, you know, all of these plots and schemes are hatched out in bars, okay. I think that's the moral of the story. And so out of these kinds of meetings, the Global Network of Astronomical Telescopes was conceived and formed, oops, let's see, I want to go back. There we go. So Eric Crane and Dave Crawford were and this is Mary Crawford, who also helped out. She unfortunately passed away here a couple of years ago, but Dave and Eric were the ones that really sort of put this together. That, okay, what we really would like to do is get a consortium of small telescopes, because there's a lot of stuff that you can do with small telescopes. Okay, well, we started out and we first of all got in contact with, it turned out that the Autoscope people, I'm again not going to name names here, but the Autoscope people had a 24-inch telescope that was in Fort Collins, and it's sited in Fort Collins. And so I was approached and said, well, would CSU be willing to site this telescope and to use it for a test bed instrument? And so, yeah, okay, sure. Well, what I didn't know is that that telescope had about 3 leans on it. And if you want to read about Autoscope, you have to go back into the 90s. Sky and Telescope magazine actually ran an article on this. Okay, I mean, and so we were all set to do the construction work for a site for this 24-inch telescope, but I had to write NASA and to ask them, well, would you release this telescope to this person? And then he's planning on siting it on CSU campus, so we'd still be using it for research and education and so on. So I wrote them a letter, the letter came back, okay, yeah, we'll release this. And then this person said, no, I'm not going to give it to you. Okay, and as I say, that's when I found out that there are 3 leans on this telescope. You know, get in line kind of thing. And so we didn't get the telescope. Okay, and the guy, as far as I'm concerned, this is well after the fact, he's a weasel. Okay, all right. Well, that's our first effort. Okay, then next was SciTech. And SciTech came along and they said, well, we'll site a 20-inch reflector down in Tucson. Okay, and Eric Crane has a roof slide-off observatory in his backyard. He's got a fair amount of property. And it's on the outskirts to the south and west of downtown Tucson. So at that time, it was a very good dark sky site. It's still pretty good. And so we started trying to do photometry with it. And I actually had a graduate student, a master's student, who worked on trying to get the photometry to work on this thing. And the summary of his master's result it could be summed up that this, the SciTech 20-inch telescope is a piece of crap. And we got experimental verification of this later on when it was discovered, and quite by accident, because Eric was shining a light through the mirror and there was a crack right down the middle of the mirror. And so, anyway, so that went down the drain. And then we now have a Meade telescope, and I think the people who've worked on the telescopes around here can tell you about all the troubles that you can run into with this thing. And at that time, Meade had a plant over in Irvine, California. And so, and during the course of the telescope, we were working the telescope trying to get tech advice. They moved that whole operation to China. Okay, so it's not there anymore. So anyway, and so basically what's happened with that telescope is we had to rebuild all the software and the guidance system in it. And we're on the verge of getting this back up online. We have some other telescopes down there that are a little bit smaller, and we'll get back to that in a way in a minute. Okay, so this is the story as of around 2000. Okay, so GNAT has been in existence for 8 years. Okay, and there really isn't a whole lot, okay, to show for it. Okay, well, along comes a very magnificent character, Roy Tucker. And Roy is he works for the Lunar and Planetary Laboratory down in Tucson, but he's a consummate amateur. I mean, he eats, drinks, and sleeps astronomy and observational astronomy. He's a superb instrument guy. And so he put together, quite on his own, and we finally talked him into getting it written up and put into the astronomical journals, what he did. And what he developed are these, let's see here. Yeah, is this what's called a Moving Object and Transit Event Search System, or MOTES. And what he's got here are 3 telescopes that are offset by about 20 minutes in right ascension. And so what they do is that they will take images in sequence, and what he mainly, the initial thing that he wanted to do with this was to search for asteroids and possibly Kuiper belt objects and comets and stuff like that. Okay. Okay, so here's the optical design. These are 35 centimeter aperture, or about 0.3 meter Newtonians. Focal lengths are matched to 1 part per thousand, 80, and so on. Here are basically the characteristics. 40, whoops, I keep getting. Let's back this up here. Yeah, 48 arc minute field of view. So that means that it's a little bit bigger than the angular diameter of the full moon. Now the idea here is that you have a simple optical design. I mean, it sounds impressive that 1 part in 1,000, but it's really not that hard to do. Easily fabricated mechanics. They don't move. Okay, they just sit there and let the Earth do all of the moving. And so it's a scan mode system. No complicated mounting. It just sits there. You get a CCD camera, which is fairly economical, and a thermally compensated. We've got these rods that are thermally compensated so that if you have expansion, that it doesn't upset the pointing of the telescope. And we got the design, and so the philosophy here is that the telescope pointing changes only rarely, and that's only when you want to change it to another part of the sky. And you spend money on only those components necessarily for the imaging process. So you've got the optics for the telescope and the cameras and the computer. And precisely pointing and tracking mounts are expensive, but collect no photons. So you spend a lot of time. And this was our experience in the 90s, is trying to get these telescopes to work, to try to get them to point correctly and all that. Again, it's just expensive, and we're not really getting anything. Okay, the observing technique with this 3-shooter, this MOTES system, to take a particular stretch of declination, 48 arc minutes of wide, just under about 3/4 of a degree, and you just point it and let the Earth scan over it. And this was where Roy did a lot of work, is that you can, then he got the computer to download at exactly the same rate that the sky was crossing the field of view of the telescope. And so at the end of the evening, you've got a strip of sky that runs the entire length of the night, 48 arc minutes across. And this is what it looks like. This is our first one. This is MG1. And so when we started using this for the GNAT purposes, we called it the MOTES GNAT telescope system, or MG system. And, oops, I have to get up here. So this is, I will get used to this. My default project is I'm warning this thing as I've got in my hand here another laser pointer, okay? So at any rate, you get a strip of sky imaged across, and we picked low declinations, right close to the celestial equator, because if we found something really good, we wanted it to be accessible from the southern hemisphere as well as the northern hemisphere. All too often, northern hemisphere astronomers, up until really about the middle of the 20th century, they didn't really care that much about the southern hemisphere, when it turns out there's a lot of interesting stuff down there. And so this is what the strip looks like. And the first of these was at 3 degrees 18 minutes declination above the celestial equator. And here are here's the observational history. We've done 6 of these strips right now. And the duration of the observations is listed here. And roughly about every 2 years we switch the declination, and so we did the low declination around the celestial equator. Then we decided to do a little bit higher declination. This includes the Pleiades. And so because Mark Giampapa was interested in the solar type stars in the Pleiades. And then the recent ones are indicated there. So this is and the last one that we finished up in July of last year. We're sort of kicking around what we're going to do for reasons that we'll talk about here in a minute. The system images look like this. The filters are standard 2.5 by 2.5 inches filters, and about 120 square degrees of night of imaging with this system. Okay, and here are the asteroid observations, and as you can imagine, okay, we're downloading something of the order of about 300,000 images a night. Okay, now that compared to the Kepler or compared to some of the Pan stars or some of this other stuff, I mean, we're, maybe AA ball players on this. But it's still a lot of images. Roy's got, he's divorced, okay, and so he has all of these CDs, okay, just a whole house full of CDs, and I'm sure that contributed. But in all fairness, he is happily remarried, okay, so at least for now. So anyway, 285,000 astrometric observations. And of that, 73,000 observations in 2005, about 8 years ago or 9 years ago. Here's the, okay.
It doesn't like you.
Apparently not.
You use the other one of your feet.
Well, now I'm going the wrong way. There we go. No, I'm still going the wrong way. Okay, now I will look at, okay, now let's see. Okay, there we go. I think I'm getting, I'll get through by the time I get to the end of the talk, okay, I'll have this thing under control, but it's too late by then. But the main thing here, over 700 new asteroid discoveries Roy made with this system. And he's got a whole pocket full of asteroids that he can submit to the IAU for naming of one sort or other. And so he's, I mean, just the guy is in his own way very, very brilliant. Okay, and they've got the moving object detection software. You like to be able to store this stuff and have it available on a night-to-night basis because this stuff adds up real quick. Okay, and so what you get here then is, here's an example of the 3-shooter. Okay, and that's an asteroid. Okay, that's at eastern end of this retrograde loop. Okay, and you can see that this is how it shows up, and it's basically a sort of a modified or a variation of the blink microscope method. Okay, the same thing that Clyde Tombaugh used to discover Pluto. And you can't do this the way Clyde did. What you have to do is get a computer to do this and to pick this stuff out. And so that's precisely what Roy and then later on Eric and another guy, Adam Krause, who was, you talk about these summer programs. We got Adam Krause as a summer student from Kansas as he was during his high school. And he worked for us as a summer student while he was attending the University of Kansas. And this guy is brilliant. He finally got into Caltech, and I got to hear all of the stories about numbers, you know, when they were filming numbers on the Caltech campus, and some great stories from that. And he then went to the Keck Observatory. Okay, well, he worked at the Keck Observatory when he was at Caltech, and then went back to Harvard, and now is at the University of Texas with a tenure track position. And he is going to be a very valuable asset to us because he has access to big telescopes, and that's going to be important for reasons that we'll talk about here in a minute. Anyway, this is what the MOTES project or the imaging does. You can pick out these asteroids, or at least the computer can. And here's a summary of the discoveries. 700 new asteroid discoveries, 3 of which are near-Earth asteroids, 2 Alton asteroids, 1 Apollo asteroid, and these are fairly important in terms of the dynamics of the early solar system, 2 comet discoveries, and astrometry on some of the NEA's near-Earth asteroids and comets. It was not very successful, at least not so far, in determining or discovering Kuiper belt objects, because those are fairly faint, and those really the big boys and girls, you know, have to look at that. And the other thing that finally happened is that about 2005, 2006, some of these big time expensive surveys, okay, so that they're going to warn us whether we're going to get hit by an asteroid or not. I've often wondered about that, just to sort of have a sidebar, that I don't know whether I'd want an asteroid to be discovered that's on the way to hit the Earth, whether it's going to be right away, okay, within, you know, say a week or 2, or if you have 2 or 3 years. Because if you have 2 or 3 years, given the way our government functions, okay, that I'm not sure that would help out at all. But at any rate, so a tremendous number of discoveries. I mean, Roy's been written up in Air and Space magazine and lots of other places. Here's Comet Tucker. And again, you can see the blinking effect here. You can see the comet moving, and it's really pretty cool stuff. And here's a close-up of Comet Tucker. Okay, that's a star in the background there, but and the resolution on the pixels is not very good. It's just sort of a fuzzy patch of light. So what finally happens to happen, at least in terms of the asteroid search, is that Roy recognized the handwriting on the wall. That he can only go down to about maybe 18th magnitude with his system, and so these other surveys can, you know, easily swamp that. And so Roy was looking around for something else that he might be able to do with the MOTES system. And we were looking around for something that we would like to do, and it was a match made in heaven. Because in addition to measuring changes of positions or motions of asteroids and so on, you can also measure variable stars. Okay, and here is a time-lapse photograph of variable stars in Messier 3, a globular cluster. These are basically RR Lyra stars. And the thing to notice here is that as these stars pulse, okay, that the image appears to increase in size and then decrease in size, so that you can not only measure motions of objects in space, but you can also measure whether they are changing their apparent brightness. And again, if you look at, well, let me pick out. Okay, one of these just about disappears. Here, this one right here, for example, if you can see this, it gets very big and then it fades out. And so you can detect changes in brightness by, again, superimposing things, you know, the background stars on each other. Okay, well, this opens it up for observations of variable stars. And you have a magnificent system for looking at variable stars, not just to discover variable stars, but to characterize them, because you're watching this every night, night after night after night, all year round. And so if you run into a star, let's say a long period variable, you can see the whole light curve. Okay, now the problem you run into is you get a cloudy night, or down in Arizona, the summertime from July and August is crap. Okay, you basically have to shut it off. Okay, and so the photometric observations then were started in 2001, and from that, from just MG1, the first MOTES GNAT catalog, these are the statistics on just one. And, whoops, back it. There we go. So, I keep slipping off of this thing. There we go. So it's about 3.5 million light curves. Okay, now by a light curve, I just mean a monitoring of a particular object's magnitude. It doesn't have to be a variable star, just, and it could be perfectly constant, and we'll talk about those a little bit. And out of this, we found that there were 50,000 in possible variable star candidates where the light from a star changed in its brightness. Now, one of the problems, and we're still kind of trying to polish this up, is that in order for that to be a viable process, you basically have to construct a catalog of stars that are in that band. And so the computer can do this. Okay, if you tried to do this or I tried to do it, you know, you'd be out the door. But you can use a computer to construct basically an atlas in that band. And then you can have the computer compare every night those same stars, and you try to get some standard stars, or at least a skeleton, okay, or a framework of stars that you can look at to sort of match up, okay, the night-to-night observations. Well, here's the story of you got 50,000 new variable star candidates. Just to put that number in perspective, that is about equal to the number of stars in the variable star catalog right now. And of these variable star candidates, it says candidates, there could be all kinds of things going wrong. It could be an instrumental problem, the thing screwed up in one way or the other. And another thing, and this was what Dave Crawford is interested in, you can get a large list of very constant reference stars. You can get stars that are constant in brightness over long periods of time, and so that's what you're looking for photometric standards. And the range that we're working in is 13th magnitude to about 18th magnitude. So we're brighter than people like Pan stars and stuff like that, and people like that, and we're fainter than what you normally have for, say, the list of photometric standards from current or previous lists. And so what you'd like to do then, okay, is to try to get some very high quality photometry for these very constant stars. Because, and you're right along the equator, the celestial equator, so you can access these stars if you're doing photometry on something else. And it's in a band that sort of slips through the cracks on some of this stuff. And so, this is then 1,200 galaxies. We go through along the equator. There are clusters of galaxies, like in Virgo and places like that. So you get to lots of those surveillances for supernova observations. And from that, we estimate about 45 observable supernova. Now, again, we're kind of out of the supernova business. But we have, again, on this particular strip, 45 possible supernova that we have observed in this context. And the importance of the supernova is that we can pick up the pre-maximum rise on this stuff, okay? At least if it gets brighter than 18th magnitude, we can pick that up. Okay, so we decided, again in a bar, okay, that this would be a superb tool, an instrument for observing variable stars in the sky. And so we set it up, as I say, and started looking in that direction. Okay, now there's 6 major classes of variable stars. They're called eruptive variables. Our corona borealis is kind of an inverse eruptive variable. It'll be at a constant brightness and then suddenly drop off about 6 or 7 magnitudes and then slowly brighten up. So that's kind of an inverse eruptive variable. Pulsating variables, cataclysmic variables, nova and supernova, rotating variables. The ELL, those are ellipsoid stars. Okay, that the star, if this is a star, that you see it edge on like this, or equator on, and then pole on, well, as it does that, there's going to be a variation, an observable variation in the brightness. And so those stars are kind of fun. And then, of course, eclipsing stars, where you have a star passing one in front of the other. And the nice thing about eclipsing stars is that you also have the opportunity to determine the size of the star from the time that the eclipse occurs and how long what the duration is. X-ray sources were out of that game. Okay, that's again we're not a player here. Okay, here's a typical light curve, and this is kind of a crummy slide. It didn't come out very well. But this is an eruptive variable or cataclysmic variable, and it's characterized by a rapid rise and then a slow decay. And depending on the characteristics of the decay, what the light does in that decay determines the class. So there's a type 1A supernova, 1B supernova, type 2, and the type 1A, I think, is it 1A or 1B that? For the 1B, yeah. The type 1B supernova are very, very good distance indicators for galaxies. They provide you an independent distance for a galaxy in addition to the redshift. And this is just by studying those kinds of stars that the people, that 3 astronomers about 2 or 3 years ago ended up winning the Nobel Prize, because what they found is that when you have the Big Bang, okay, the conventional wisdom was that the Big Bang starts out expanding very rapidly and then slowly slows down because of self-gravitation. Okay, well, what these guys found is that, okay, you know, if you throw up, let's see, I don't have a, oh, all right, my car keys. If I throw my car keys up in the air, okay, they slow down and stop. Okay, but what they found is in the Big Bang, if I throw the car keys up, they accelerate. Okay. Yeah, and so how does that happen? Well, enter dark energy, okay? And enter a whole new era in cosmology, because there's all kinds of neat stuff. But at any rate, one of the things then that that the MOTES, the MG system can do is to catch these supernova on the way up. Okay, and here's one. This is supernova 2005. And the discovery date, when it was first noticed by the big boys and girls, was on June 8th of 2005. In one of the galaxies that we were, it was in the strip. And if you look, these are all observations made by the MOTES, and so you get a very nice pre-nova, pre-maximum curve on this. And unfortunately, again, our limits are somewhere around 18th magnitude. So we can't say what happens down here, but at least here is a very nice portrait of the rise and magnitude of a supernova. We haven't really looked at some of the other stuff. As I say, we estimate there's about 45 of these things that are in the MG1. Okay, the other, another type of variable we talked about, had up before, is a pulsating variable. And what happens here is that the star actually changes its size. Okay, and when it changes its size, it changes its brightness. Okay, so here's the brightest, and then it collapses and then increases, and so you get essentially a pulsating effect. And there are some very important stars that are pulsating stars, Cepheid variables, for example, are Lyra stars. And in particular, we've there's a phrase in science where you pick the low-hanging fruit. Okay, and what we've done in this case is to pick out long period variable stars, because they show up, their light curves show up very nicely. There's not a bunch of scatter, and we'll show you what that looks like here in a minute. And so here you have, this is one of the MG1 LPV, long period variable stars, a period of about 171 days, and you can see clearly that you have some very nice coverage in terms of the light curve of these kinds of stars. And we started out with about 65 or 70 of these things and decided some of them were irregular variables and semi-regular variables, and so we pared it down, and so we're just in the process of sending a paper into the AAVSO where we've actually 45 new long period variable stars with where you can characterize the light curves in this fashion. So, and that's okay. I mean, it's nice to have a few more variable stars and to discover stuff that nobody's seen before. But it turns out that in about, maybe 10%, let's see, probably about, more like about 25% of these variable stars that we looked at have a feature that people have alluded to once in a while, but it's a hump feature. So this should be coming down like that, but it sort of bops up like that. And a close-up of this looks like this. I think you can see it a lot better. And so if the star is increasing in brightness, you would expect that the light curve should look something like that. Well, it doesn't. It looks like this. And so these features, as far as I'm aware, nobody has at least discovered them to the extent, I mean, they said they've sort of identified it as a single anomaly or something like that, but we've found them now in 10 of these new variable stars. And so it's going to be fun to see how the theoreticians deal with that. We've also, unfortunately, we look for flares. One of the questions surrounding long period variable stars is, do they flare? Let's say like the sun. And the best we've been able to do is flare event question mark. Okay, so flare event, okay, kind of thing. And that's it, that's been it, okay? And that is a questionable one because it turned out that the night that this thing reached maximum, the next couple of nights were cloudy. Okay, and then I mean, this is a well-known effect in science, okay? And so the when the flare was done, okay, then it cleared off, okay. Well, what a lot of times in science, a null result is very important as well. And so we were able to, we have 45 long period variables. We have very good temporal coverage of these things. And so we can begin to put into play some statistical analysis. And Richard Eicholt up at Colorado State, who's, by the way, a resident down here in Berthoud, I think that's how he is able to survive. He comes down here, okay, and he doesn't have to deal with some of the stuff up at CSU. But anyway, he did some statistical analysis of these things, and the flares are not very, very common, if at all. Whereas on the other hand, the humps, okay, this could be a very significant kind of phenomenon, and it's going to be interesting if we go to the other strips, or as we're going to see, we'll return to the original strip, and if we can reproduce these after about a period of 5 or 6 years. So lots of interesting things with the long period variable stars. Here's an example of one of our light curves for a pulsating star, which is a shorter period. This is actually a Cepheid variable with a very long period for a Cepheid. Usually Cepheids are of a few days up to maybe a couple of weeks. This is a very long period Cepheid variable, and for that reason it's very interesting because the Cepheid luminosities are dependent on the period. So the longer the period, the bigger the luminosity. And so this right away becomes a very interesting kind of object. Then are eclipsing stars. And this is where one star passes in front of the other. And there are a whole bunch of possibilities. You can have a partial eclipse up here where part of the stars are eclipsed, and so you get the kind of pointy light curves. And most of the time the light is steady from these stars. You can have a central eclipse, okay, where the star passes in front of the primary star, and you get these deep eclipses and then a flat bottom, okay, and then this is, whoops, you get a flat bottom, and from this descent and from this flat bottom, in fact, I just had a final exam question in my astrophysics course, having a curve not terribly different from this, in which they had to figure out what the radius or the diameters of the stars were, which is fairly easy to do. Okay, you can have a star that's ellipsoidal in shape, okay, where you get a fairly close contact star where you don't get this nice flat equilibrium position, but you get a constant waviness. And so here's the secondary eclipse, here's the primary eclipse. And then sometimes you can have a hot spot on the star, okay, and so you get this kind of a curve. And so if you can get a light curve for an eclipsing star, you can tell quite a bit about the star. And here's an example of one of our eclipsing systems. This is a star which has a primary, and a lot of these are very rough data, okay, but you get the idea. Here's, it looks like a secondary eclipse, and here's a primary eclipse, and so this is, by the way, this is a phased light curve, so that's, and the period of this is 16 days in this particular instance. And so with these eclipsing systems then, one of the things that was done was to look at these candidates, these eclipsing system candidates, and to see if we could get some additional information just out of the standard catalogs. And it turns out that the MASS catalog, which is a microwave catalog that does photometry in the JKL bands, which are in the kind of in the far infrared. It turns out that a number of these systems, in fact 121 of them, had very, very red colors. And so the top curve there is a raw light curve from the MG1 catalog, which you can see here's an eclipse there. And so this is where Adam Krauss came in. He was at Caltech. He had time at the Keck telescope and was able to secure spectral types for these stars. These are very faint stars, these M dwarfs. And so they have absolute magnitudes that are of the order of about plus 20, which means if they're 30 light years away or so, they're 20th magnitude. And the thing is that there are a whole bunch of these things, but they're very faint, and so they're tough to find. So anyway, this is a spectrum of one of these stars, and in fact, this particular one. And the interesting thing, and the reason that these are of considerable interest to astronomers, is that if you look at a plot of the luminosity of stars versus their effective temperature, and this is a logarithmic plot here, okay, so that it's not a linear plot, but you find most of the stars in the sky, about 90+% of them, lie along this sort of curvy band called the main sequence. And if you get down here, these are the red dwarfs. You get down here, you're looking at stars that are maybe 10 to the -5 luminosities. Okay, 1/100,000th of the luminosity of the sun. Temperatures that are in the around maybe 2,000 kelvins. Okay, and in fact, some of these stars are so low temperature that you can see steam in the spectrum of these stars in their atmospheres. Okay, so what you can do if you measure the radial velocities of these systems, which you can do with these M dwarfs, and with you have a big telescope, and this is what Adam Krauss did. You can measure the duration of the eclipse. You can measure the masses of these stars, radii, and so what we were able to do is to add, okay, if you go down to the lower end of the main sequence, which is this line here, there are 1, 2, 3, 4 stars that were down in these kinds of luminosities and masses, or mass radius, and we basically doubled the data points in that part. And we still have tons of these things to look at. But what we need now in this case is access to another big telescope where we can get radial velocity measurements and so on. Okay, here is a shorter period variable star. This is a contact binary that runs up and down, and you sort of get a sine curve. These are very short period stars, and you can see that the period here is about 1/10 of a day. But this makes it nice for student exercises, because now you can have students take a look at these things. The periods are short enough, so you can just keep on observing the star. Let's say you start off at 6 o'clock at night and you go until 1 or 2 o'clock in the morning. You've covered, in this case, 1/10 of a day is about 2 hours for the period. And so this is at Cuesta College, which is out in San Luis Obispo. It's a community college, and these are some student photometric observations. And this is what they did was set on a constant, or to set on a standard star or a constant brightness star. Okay, and that's this observation. This is the target star, which we gave to them. And so this is how they published it. And now what you've got here is these are the observations in a single night. Now what happens, of course, is that you've got some coverage that you don't have because it's daytime and the star is set. Okay, and so one of the things you'd like to be able to do with these stars is to somehow observe them throughout a whole cycle. And here's the light curve that they published on this particular star. And so what you'd like to do then is to get constant coverage. Well, how do you do that? Well, you get a global network, okay? And so it finally seems that we are approaching finally, after 22 years, a global network, because the future history of GNAT, and I borrowed that term future history. There's a very well-known early 50s science fiction movie called The War of the Worlds. Okay, and at one point this guy is narrating into a recorder, and he says, so that means these recordings are for future history, if any. Okay, and so I've deleted the if any there. Okay, but it's really starting to come together. Okay, the first thing is we mentioned a possibility of additional MG strips. And we can do additional declination strips. There's a possibility that we can do these things with a polarimeter on the edge of the telescope, so you can find which objects have highly polarized radiant energy. 3 color observations where you put photometric standard filters, usually a visible, infrared, and red, the VRI filters, and then objective prism observations where you put basically a prism on the front of the telescope, and so the light from the stars gets broken up into its component spectra. Now the problem there is that you can only get the brighter stars, but it's this kind of an observation that had the SS catalog, which gave us SS 433, which is the first indication of a black hole or a black hole type object where you're shooting these relativistic jets out. And then obviously follow-up photometric and spectroscopic observations of interesting variables. And there is a gazillion of these. And one of the things that we're sort of looking for is for people that might be interested in doing that. It's it's hard work, and you have to stay with it. But anyway, we've got a couple of telescopes down in Tucson that aren't. They're about maybe 12, 14-inch telescopes. We're tapped into a robotic system at the University of North Carolina, so there are some possibilities there, and they're fairly interesting. If we ever get the Meade 16-inch going down in Tucson, that's going to be very nice as well. We talked about, whoops. Okay, let's try it again. Okay, develop a catalog of photometric standards, 13th magnitude to 18th magnitude. If we can do that, I mean, talking about years of observations here, okay. And worldwide NAT coordinated observing team to investigate short period variables in eclipsing system, and truly a global network. Now, we're on the way to that. We have observing groups down in Cordoba in Argentina. We have a person down in a group down in New Zealand, the North Island in New Zealand. We've got we have a person in North Carolina doing observations. Tucson is doing observations. And so we have a little bit, not as complete a coverage as we want, but we can follow a lot of these stars. And so we're getting to the point where we're going to have, the variable star of the month, where you put out the finder chart and the star, and then people are supposed to observe it as much as they can. And so as some examples here, okay, here we're working, this is Roy and Eric Crane and Roy Tucker. Roy and Eric working on the 16-inch, okay, and this is another shot of the 16-inch. You get an idea of what we have in terms of the facility. It's a roll-off roof. You can see the saguaro cactus, okay, in the background. Okay, there. And then this is, I don't have anything labeled on this because this is a very preliminary light curve for one of the eclipsing systems that we've been observing worldwide. And you can see that we're starting to get some really good light curves. But the problem is that different people are using different standard stars, and that screws everything up. And so we're going to try to clean that up a little bit and redo the, I mean, we've got the images, but to do the reductions, you need to do that. And this one looks like it's a, it's a minimum, and there might be star spots on here. I mean, so there's all kinds of neat things. And so one of the primary reasons that I'm in this, okay, is because A, I like astronomy, and I want to do astronomy even after I retire from CSU. And this is one of the things that will help keep me off the streets. And believe me, Andrea will tell you that's what you want to do, okay? And certainly my wife Gail will as well. So anyway, that's an astronomical consortium where it's, as they say, it's a modest, it's a small-scale operation. It's not like Pan-STARRS or Kepler or any of these other things. And the nice thing about it is it's cheap, okay? I think we've done this virtually without any outside support. There have been a few $1,000s come from our dean at CSU, Jan Nerger, and a couple of other donations. But I mean, I would love to, for example, just have the bar bill from the James Webb telescope, to be perfectly honest. Okay. Okay, any questions at all? Yes, sir.
How do these, the star maps that you have there, how do those correlate? Check those against what Kepler's finding?
Well, Kepler is centered on a very small area of sky in Cygnus. Okay, and that's at a very high declination. So it's way off of what our strips are. Now, a question similar to that would be, have we been able to recover known variable stars in that strip? And the answer is yes. Okay, we've been those have showed up very nicely. So we're at least doing something right.
But I know that they use the same technology or method of looking at the eclipses.
Oh, sure. Oh, yeah. I mean, well, they're downloading about 4 million images a night. We're doing about maybe a tenth of that, if that. I mean, more like about 300,000 images a night. So again, we're like AA ball compared to the major leagues. Yes, sir.
Can you get the orbital elements of asteroids from your
Yeah.
information?
Yeah, all you need are 3 independent positions. Now, the orbit might not be that good because you might not have a big enough arc, okay, but you can certainly get a preliminary orbit. You bet. Yes, sir.
Can you, seem like you find planets for this arrangement?
It depends, again, on the eclipses. I mean, in theory, if these eclipses are shallow enough, and there are a lot of ifs, but yeah, it's possible. I mean, that's one of the ways that exoplanets are being discovered is by Kepler's watching eclipses, and also other ways. The other way you can do it is by looking at the variations in the radial velocity. So, for example, on these M dwarfs, okay, those are very low mass stars, and so they can be presumably influenced more by, say, a Jupiter-sized planet, or even a little bit smaller. And so, if you look at the radial velocities of those systems, it might pop up. I mean, you never know what it's like eating a box of chocolates, okay, And that's what's so much fun. I mean, it's great going through. I'm only one of 3 people who've gone through all 50,000 images on these and sort of tried to sort them out by eclipsing systems possibly and so on. And it's just great fun. And it's just, we're still in business, okay? It's 22 years and it's looking pretty good for NAT. And again, I'd love to have the bar bill from James Webb Telescope. Just to put that in perspective, I was at the AAS meeting in Indianapolis last summer, and I went up to the James Webb booth, okay, and I said, well, and keep in mind that the James Webb Telescope was initially budgeted at $1.5 billion. Okay, and so I went up to these people, and they still haven't got this thing operational, and the cost is now up to about $8.5 billion. And so I said, $8.5 billion? Well, my God, you guys can waste taxpayers' money just as readily as the military and the social programs people, And so it's just, You know, as I said, I'd love to have just some of that. All we need, you know, maybe a few tens of thousands of dollars, you know, which is, as I say, nothing. Okay.
Thank you.
Oh,